Hi everyone, my name is Emily and I'm coming to you from my basement in Boulder, Colorado, so hello. And I also wanted to say before we start, thank you to everybody listed here for their phenomenal help with writing this paper. So to get into it, the problem that we're looking at is suppose a student is asked to regulate their own learning in a self-paced learning environment. So this means that they don't have a teacher necessarily telling them what to do. This could be in one of those MOOCs or a massive open online course or something similar. And so if we look at what the research tells us is an appropriate way to use your time, we come across maybe something that looks like the ICAP framework, which is we prefer students to kind of land on this more interactive side of the spectrum, and then from in decreasing level of effectiveness, we get to what students usually do when we let them loose to manage their own time, which is something more along the lines of the passive activities such as watching videos or highlighting your textbook or something like that. And so if we want to get more specific for the purpose of this paper, we're looking at something called retrieval practice, which has been shown in a lot of studies to be really effective for long-term retention, where students practice retrieving information from their memory. So this could look like flashcards or quizzing yourself or coming up with little tests to make sure that you know the material. And these are all really effective ways to practice that. But we tend to see that students get really caught up in this like cramming and memorizing right before an exam. And so for this paper, we propose a workflow for especially these online learning environments where students start by interacting on whatever platform you're looking at. And then we have some sort of estimate of quiz success. So if we have these assessments built into our platform, it would be really great if we had an opportunity to understand, like, is a student going to be successful if they try to take a quiz right now? And then ideally in the future, we'd like to develop some sort of intervention to say, hey, we think that you would do well on a quiz right now. Let's not waste any more time and let's get to it so you can move on. Or maybe you need to spend some more time studying before you maybe attempt to quiz yourself on this material. And then finally, based on the intervention, a student may take the quiz and then we can go right back to the beginning. And of course, this isn't an ideal world, so sometimes the student may choose to not take a quiz. And so then from that intervention, we may just go straight back to the beginning and continue monitoring. And so for the purpose of this paper, we're really focusing on that second step, which is providing an estimate of student quiz success. And our specific data set that we're looking at is for a high school algebra platform, which is online. And so the first question is, what kind of granularity are we looking at when we're trying to make these predictions? And so we have a really wide range that we can look at, going from very fine to very coarse. And so I will put a few references on the slides, but there is a lot of prior work along all ends of the spectrum, so you're welcome to look at the paper for more details on these. But on the fine side of the spectrum, we have previous work that's looking at predicting whether a student is going to get a particular item or question correct, or something along the lines of a programming problem. And then on the complete other side of the spectrum, we get something like predicting how a student's going to do on a long exam, such as a final, or how well they're going to do in the course overall, or whether or not they're going to drop out in general. And so for these smaller items, we think that these aren't really informative because this is just on like an individual item. It's not really giving them any idea on how they're doing as on the topic as a whole. And then on this other side of the spectrum, these are really high stakes. And while there is work looking into early detection of dropout, for example, sometimes it could be too late to have an intervention, or maybe we don't have an interpretable understanding of why they're at risk, so we can have an intervention for that. And so for this paper, we split the difference and are looking at predicting how students are going to do on a short quiz, namely using the activity that they have leading up to that quiz. And so specifically, we're working with an online platform called Algebra Nation, which is an algebra learning platform. And the data set that we're using is made up of students all across the state of Florida. And so the ways that students can interact with this platform is primarily through expert tutors. So for each topic, students can choose from a variety of tutors that go through the topics in as much detail as they want. So some tutors specialize in very specific, very detail-oriented explanations, while others are more high level. They can also take quizzes that either are multiple choice or free response questions, or type in the calculator type of questions. Some teachers may choose to assign these as homework that goes along with their regular in-class instruction. And then students can also post questions on the discussion board if they get stuck on a problem or don't understand some of the concepts. And so these questions can be answered by the expert tutors or by other students on the platform. And then if you answer another student's question, you can also earn some bonus points as well. And so the data that we're looking at, we have about 32,000 students that we have data for on this platform. And our goal labels that we're going to try predict through this machine learning process are their quiz performance. And so, like I brought up before, we're focusing on these short formative style quizzes. And how this looks on the platform is there's a variety of formats, but each of these quizzes has 3 items or questions. And then after the students take the quiz, they have the opportunity to see if their answers were correct and to review that topic in more detail later. And because they can go see the answers and take the quiz again, we're only looking at the first attempt because we know that they will probably do better the second time. And so we're just looking at how they're going to do based on the studying they've done up until that point. And so we have about 210,000 quizzes that we're looking at in our data set. So in order to predict those quiz labels, we have our interaction click data are the features that we're putting into these models. And so the reason why we chose these is that they're really scalable. So we can use them on a really large platform. Like we said, we're looking at 32,000 students and they don't require any extra sensors or the like. And so a quick overview of how we build our instances. We start with a quiz. And then to start off with, we looked at up to 3 minutes before the start of the quiz. So once they started the quiz, we don't really care about what activity that was. We're just looking at what happened before that. And then they can do a variety of actions leading up to that quiz. So that could be like playing and pausing a video, rewinding, maybe asking a question on the board if they don't understand. And they can even work on other quizzes in the meantime that aren't related to the current quiz. And so what we do is we aggregate these. We just take a simple count of how many times each action happened leading up to that quiz. And some details about our model building. We used a random forest regression model, and our goal was to predict a quiz score. So since these are 3-item quizzes, our possible scores range from 0, where they were all wrong, to 3, which is 100% correct. And for this problem, we used student-level cross-validation, which means that when we were splitting our data into the training and testing folds, all of one particular student's data can be found either in the training or the testing fold so that we don't get any bleed over of their information. And we hope that this makes this more generalizable to other, as we apply our models to other students as well. And so the results that I'll be presenting here are using the Pearson correlation between our predicted and actual scores. And so how, just as a reminder for correlation, that goes from a score of -1 to +1, whereas 0 is no relationship. And so our first research question that we came to, just to start off, is how well can we predict quiz performance using the immediate learning context? And so what we did is we took our interaction click data, which I just described, we fed that into our random forest regression model and came out with labels on quiz performance. And so this initial model gave us a Pearson correlation of 0.42. So that can be kind of our baseline model that we're going to compare everything else to. And so since we're really interested in quizzes and we know that retrieval practice is helpful, this led to our second question of what is the influence of prior retrieval practice on quiz performance? And so how we did this is we took our interaction click data, which is originally 22 different features, and we split it into features that were related to quiz activity. And this isn't on a related topic. It doesn't have to be. It's just any quiz that may have happened in the preceding time window. And then we also split off any activity that wasn't related to taking previous quizzes. And so we built two separate models here. We took the quiz-only activity, put that through our random forest regression to predict quiz performance. And we also took non-quiz activity and trained a separate model using those features only. And so in this case, we found that quiz-only activity gives us a correlation of 0.41, which is very similar to the original model that we found. And our non-quiz activity gave us a correlation of 0.33, which is, while still better than random, and so it's giving us some sort of signal. It looks like this quiz-only activity is actually giving us a pretty good signal compared to all of the features together. So then the next question was, how well can we predict quiz performance using context-independent features? So up until this point, we've only looked at these immediate activity features of what the student was doing right up until they started taking the quiz. And so to answer this question, we introduced a couple new features into our model. And so based on prior work of our collaborators, we've developed an item response theory 2PL model, which is a statistical model that allows us to get some information about the items that are present on Algebra Nation. And so out of that, we have an estimate of item difficulty for each of the questions on these quizzes. And what we've done is, because each quiz has 3 questions, we've averaged that item difficulty over the 3 items on the quiz to get some sort of estimate of quiz difficulty. And then the second feature that we got was, out of this item response theory model, we can get an estimated ability of the student for a given section. So think of it as like a chapter in a textbook based on their responses to previous items leading up until this point. And so what we've done is we've averaged this estimated section ability over the 10 sections to give a snapshot of student ability in general over the platform for a given time period. And this will change over time as students take more quizzes and we get a better idea of how they're performing. So to go back to our research question, we took these 2 new features, quiz difficulty and student ability, and we fed these into our random forest regression model, again, to predict quiz performance. And we found a Pearson correlation of 0.34, which, to put that into context, was about the same as using those non-quiz activity features. And finally, just to see how we can do by combining both of these context independent and the immediate learning context features, so those 2 sets of features that I've talked about so far, if we take all of those together and put them into our random forest regression model, we can predict quiz performance with a correlation of 0.53. So to put that into perspective, that gives us an R-squared value of about 25% of the variance we can predict with this model. And this is the best result that we got out of all of the feature combinations that we tried. So to push this a little bit further, we asked the question, how much context is needed to predict quiz performance? One of the rules of thumb in the machine learning community sometimes is that more data is better, or maybe if we take more time leading up to the quiz, we can get an even better idea of how well a student's going to do on this quiz. And so just to flash up this instance building slide again, what we did is we actually varied the amount of time leading up to the quiz. And so we looked at their activity counts for various time periods before that. So in total, we looked at 4 different models. Our original that I've discussed so far is using this 3 minutes of data leading up to the quiz, but we've also looked at 5, 7, and up to 9 minutes leading up to the quiz. And we actually found that there is no significant difference as this time window increases. And actually, once you get to the 9-minute mark, our performance starts to erode a little bit, probably because 9 minutes is relatively long compared to the amount of time that students spend on the platform. And there's a lot going on in that time. So our signal's probably getting quite noisy. And so finally, our last research question that we had was, which features are most influential for predicting quiz performance? Because can give us an idea of what to look for when we're either designing future platforms, or how can we support students and maybe nudge them towards the activities that will actually be helpful for them. And so to do this, we looked at our model that used that interaction click data plus the 2-item response theory features, because that gave us the best performance overall. And so we first trained a random forest regression model, but we also trained a linear regression model because the coefficients for the features are more interpretable in this case, because it gives us assigned value, positive or negative. And so for each of these, we predicted the quiz performance, and then we pulled out the top features for our random forest regression model, which is able to really model those nonlinear relationships between our variables. But then we'll also give you the coefficient values for the linear regression, which pretty closely follow the random forest, but gives us again, a positive or negative indicator of whether these tend to be better or worse for student quiz scores. So our top feature that was predictive of student success on a quiz was viewing an incorrect item, which is interesting because this incorrect item isn't necessarily for the same topic. It's just any other previous quiz if they're looking at what they did wrong. This is a positive indicator that they may do well on the next quiz. And then our next two are quiz difficulty and student ability, which are interesting because these aren't related to the activity that they had on the platform up until that quiz. And then finally, loading the discussion board had a negative relationship with student success on the quiz, which is interesting to think about more and maybe indicative of maybe shallow processing of students, like looking up answers and not coming up with solutions for themselves, but could warrant more thorough research into that. And then finally, answering an item in general, again, this doesn't have to be on a related topic or anything, is also negatively correlated with student success on the upcoming quiz, which could be a sign of cognitive load or fatigue or something like that. But these are, again, interesting to look into in more detail in the future. And so to start to wrap up, I wanted to talk about some of the applications that we can use with this work. And so, like I said at the beginning of this talk, we proposed this little workflow here of students interacting and giving them interventions. And I think that future work really needs to look at this intervention part to see, are students even going to use these? Do they see them as valuable? And then really importantly, how do we design interventions so that they're not harmful to students? Because we know that our models are never going to be 100% accurate. And so if we say to someone, we think you should take this quiz because we think you'll do well, and they don't do well, that can be a really big hit for motivation and self-esteem and all of those things. And so how do we design interventions that also do no harm to our students? And so in summary, I and my colleagues proposed an intervention workflow which provides nudges to students that they can use as a reminder to use retrieval practice as a study strategy, because we know that's effective. And then as a first step towards this really big goal, we show that we can use machine learning plus interaction patterns from our online platform to predict how well a student will perform on a quiz, namely before the quiz starts, which is really cool. And this doesn't require us to use a really complicated statistical model of learning or expert created knowledge components that comes up in like the Bayesian knowledge tracing. but it is aided by those types of statistical systems as well. And so I wanted to say thank you and to all my collaborators at various institutions. And I am ready to take any questions you might have.
Great. Thanks, Emily, for that very interesting presentation. So just a reminder that if you do have questions for Emily, just to pop them into the Q&A on Rover. There is a question already, which is from Camilla. Do you want to unmute yourself and ask your question?
Sure. Hi, thank you so much for your presentation. I had two questions. So the first one was, why are you only looking at 9, or more like, what is the rationale of only using 9 minutes of interaction data and not take the data from the entire time, since the learner has either signed up on the platform or, started the course?
Yeah, that's a great question. So part of that comes from a trade-off between more data as far as a longer time period and the amount of time that students are spending on the platform. So actually the session lengths that we're looking at, students aren't on the platform for very long at any one time. And so if we start to look at windows longer than 9 minutes, then we start losing a lot of students because we don't even have quizzes that have that much activity leading up to it. So our data set would get significantly smaller if we kept going that long.
Got it. Thank you.
Mm-hmm. I think you said you had a second question.
Yes, I did have a second question. I just wanted to see if anybody else wanted to jump in. My second question was, I saw that in your list of features, you called out student ability, and I hadn't read your paper yet, but how do you, in this context, measure student ability?
Yeah, so student ability comes from our item response theory model. So based on student responses to previous items, we can get an estimate. I'm definitely not an expert on the item response theory, so I would probably direct you to my collaborators that actually worked on developing this model. But we can use it to basically get an estimate of student knowledge in a specific area based on the items that they've answered specific to that area. And so what we've done is rather naively just average those over all of the sections to get a general idea of how well they're doing in the course in general.
Awesome. Thank you so much.
We have another question, actually I think 2 questions that Camille has posted. Camille, did you want to unmute your mic and ask Emily your question?
Okay, yeah, I can ask directly. So first question is, can you elaborate on why you selected Pearson correlation as the performance measure? And I wonder if you try to do any feature selection and then see if it improves any performance on your modeling rather than, putting those all features together in the model and then just checking which one predicts better. I just maybe get some insight about those things. Thank you.
Yeah, just to address the feature question. So the way that, I guess we didn't exactly choose the features. So these are all of the various activities that we can get logs from the Algebra Nation platform. So we have a grand total of 22 actions that we can measure from students on the platform. And so we used all of those. And we didn't do much of like a feature analysis from that perspective of maybe choosing a subset or feature engineering. So this is, I think we probably mentioned this in the limitation section, is like it's a pretty simple approach of just counting up actions, and we didn't really look at any like patterns between them of like what order they did the actions or anything like that. And so I think that's a really good area to look into next. And some of the papers that we referenced in the related works have done some interesting work on feature engineering as well that could be looked into in the future. Regarding the Pearson correlation, that was due to like the distribution of the data that we had. Since I'm like right up until my bedtime, I can't give you a great answer for that right now, but we do discuss it in the paper if you want to look at that in more detail. I don't want to get that wrong on the record.
Okay, thank you very much.
Yeah, thanks.
Wait, there's another question for you, Emily, from Felix. Felix, did you want to unmute and ask your question?
Thank you very much. Very good work. My question is, could there be other variables that might affect quiz performance?
Oh, absolutely. Yeah, I would not be surprised by that at all. So there's some other kind of features that we've looked at in other work, not specifically for quiz prediction, that I think would be really interesting. So some things we've looked at are time of day. So are students doing this like during school? Are they doing it after class? Are they doing it like right before their bedtime, right, where they're not functioning at their best? And there's so many other things in their like context of, are they taking this at home during COVID and they have family stuff going on? So I'm sure there's definitely a lot of other factors that could go into this.
Great. I think we have time for one more question. Nina had a question. Nina, did you want to unmute and ask your question to Emily?
Sure. Can you hear me okay?
Yes.
Yeah, I can hear you.
Okay. So I remember you listed a top maybe 5 or so variables from both the random forest and linear regression model. I want to first is to understand whether those are the same. Did you see the same top variables from both models? And question 2 is, how do you interpret the different coefficients? If I recall correctly, I saw some are, for some variables, for example, some are negative in linear regression, but positive in random forest, and I just wonder how to interpret that.
Yeah, that's a great question, and I definitely did not go for that in enough detail. So the random forest, they're all positive coefficients that add up to 100%. So this is a relative importance out of, I guess mine were decimals, so they're out of 1. So a higher number means more important, but we don't get that signed importance, which is why we put it through the linear regression. And so the linear regression is a little bit more interpretable, where a positive coefficient means basically, let's see, if we're talking about like student ability, it has a positive correlation. So we say that students with a higher estimated ability tend to have a higher quiz score as well. And then your question was whether they matched between the two models. We talk about that a little bit in the paper. They're not a complete match, but the top 5 definitely are have a lot of overlap, and those coefficients that are higher in random forest tend to also have high, or like larger magnitude coefficients, not necessarily positive or negative with our linear regression model.